The European Organization for Nuclear Research's collider has proven something so strange, so seemingly impossible, that it changes everything we thought we knew. Scientists at that underground lab smashed particles together at incredible speeds and caught the heaviest ones, the top quarks tangled in a way that defies what should be possible. Tune in, because what they just confirmed could mean the key to controlling the very fabric of space and time is finally within reach. When particles break the rules, back in the 9th month of the year 2024, the big machine at that underground science lab in Europe did something wild. The researchers there, who smashed tiny bits of the universe together at unbelievable speeds, observed something never seen before at such a high power level. They caught two of the heaviest known particles, the top quark and its counterpart, the top antiquark, getting entangled in a way that makes no sense if you're thinking in traditional physics terms. This was the kind of weirdness that legendary. Scientists once debated, and now, with this machine generating energy levels through the roof, it's happening in full view. That's when the numbers stopped making sense, and the real mystery began. If you've never heard of this whole entanglement thing, it's when two particles act like they're connected, no matter how far apart they are. Change one, and the other reacts instantly, faster than any signal should be able to travel. It's one of those mind-bending concepts from quantum mechanics. Some scientists once dismissed it as nonsense. Others believed it was the key to the future. Now it turns out it's real. And these massive machines are proving it again and again. Until now, people had experimented with light particles and tiny electrons. But this is a whole new level. Let's talk about these top quarks. If particles were cars, top quarks wouldn't be hatchbacks. They'd be massive 18-wheelers hauling heavy loads. They're about 173 times heavier than a proton, which is astonishing. But they don't stick around for long. They pop into existence and vanish almost instantly, transforming into other particles. That's what makes them ideal for experiments. Like this, their information doesn't have time to get scrambled, so scientists can analyze them in their purest state, just as they were at creation. If you want to test quantum entanglement in high-energy situations, these are your go-to particles. Edit. The massive detector inside that underground collider, scientists put the idea to the test. They focused on what happens when two top quarks and their opposite twins, the top antiquarks, are created during high-speed collisions. The goal? See if these pairs are linked in a way that can't be explained by classical physics. To do that, they examined something called spin. Spin is a property of particles that resembles rotation, though not in the basketball sense. It's more like a built-in directional quality. If two particles are entangled, their spins should be locked together in a way that breaks ordinary expectations. That's exactly what the scientists studied, how the spin directions lined up when the particles separated. They checked the angles, measured directions, and ran mountains of calculations to determine if the spins told a story of entanglement. The results were crystal clear. The numbers matched what quantum mechanics predicts when entanglement is in play. The key measurement, called D, had to be less than 1.3 to prove entanglement. The final result? 0.537. That's not just under the threshold, that's way under. This wasn't a fluke, it was the real deal. Why does this matter? First, it's a huge win for the rulebook of physics that explains how the universe works on the tiniest levels. Every time an experiment like this confirms a theory, it strengthens the foundation of modern physics. But even more exciting, if the numbers hadn't lined up, it would have suggested something even bigger is going on. Something we don't understand yet. And that's what gets physicists truly excited. They look for gaps in the rules because gaps mean there's something new to discover. This finding also opens the door to more extreme experiments. If entanglement happens at this energy level, what about heavier particles? Could the famous Higgs boson, the one that gives everything mass, get entangled too? And what would this mean for quantum technology, like the computers scientists are developing that rely on entanglement to perform calculations far beyond what traditional machines can do? Bottom line, this was a huge moment for physics. The invisible. Rules governing the universe were tested at the highest energy levels ever, and they held. But there are still big questions left, and the scientists behind this work are just getting started. So how did they actually pull this off? The detector used in this experiment is among the most advanced machines ever built. It was engineered to catch and analyze what happens when tiny particles smash into each other at nearly the speed of light. The energy involved in these collisions is immense, 13 trillion electron volts. That level of energy doesn't exist naturally anywhere on Earth. It's like recreating the first moments after the Big Bang. Spotting entanglement in that chaos is no easy task. Top quarks appear and vanish almost instantly, leaving behind traces that scientists must reconstruct. They don't see the quarks directly, they see what they decay into. By measuring the angles and paths of those decay products, researchers can determine what the original quarks were doing. To confirm entanglement, they compared data from thousands of collision events. This wasn't a lucky accident, it was a pattern. Over and over again, the numbers pointed to the same conclusion. This is a breakthrough because top quarks exist in a state closer to their pure quantum form than nearly any other particle. That gives researchers a cleaner look into the true nature of reality, and this is just the beginning. Now that entanglement has been confirmed at these high energies, future experiments may reveal even more. Scientists are already planning to see whether other particles can become entangled in similar ways. There's also the possibility of practical applications, like using entanglement to revolutionize quantum computing. If researchers can learn to control entanglement in high energy environments, it could redefine how quantum information is processed, and that's only the beginning of how this science hub came to be. The European Organization for Nuclear Research, located in Geneva, Switzerland, is the largest playground for physicists in the world. Originally a European dream, it has become a global powerhouse. If you've ever wondered what the universe is made of, this is where they're trying to find out, one smashed particle at a time. Back in the late 19th century, science was reaching a turning point. Joseph John Thomson discovered that atoms weren't solid little balls. He identified electrons, showing that atoms were made of even smaller parts. He imagined a plum pudding model, positively charged matter with negatively charged electrons floating in it. Then came Ernest Rutherford, who tested that idea by firing alpha particles at gold atoms. Most passed through, but some bounced back. That meant atoms had dense cores, the nucleus. This discovery kicked off the idea of smashing particles to uncover the secrets of matter. Fast forward a few decades, after World War II, science in Europe was in crisis. Many top scientists had moved abroad. Louis de Broglie proposed a solution. In 1953, 11 countries agreed to build a massive physics lab. By 1954, the Nuclear Research Center was born on the Swiss-French border. The mission: build powerful accelerators, uncover matter's secrets, and encourage global collaboration. With one rule: no politics, only peaceful, transparent science. They started small. The first machine, the synchrocyclotron, went live in 1957. Then came the proton synchrotron in 1959.